Hi, in this video we are going to explore the keyboard interfacing with PIC18 microcontroller. We see that 4x4 keypad interfacing and unlocking user input. We know that the keypads are essential for human-machine interaction in embedded systems and any other IoT devices. They provide a cost-effective and reliable way for users to input data directly. And we have to find the keypad interfacings are everywhere from security system to smart appliances. So first we have to empathize the keypad interfacing with our daily interactions. Imagine entering your PIN at an ATM or setting the time on a microwave. Users expect instant and accurate responses from the keypad. The input directly controls devices functions like unlocking smart door. We know that for unlocking that, user input as pressing a key, and microcontroller automatically detects the pressed key, and the device action is the pressed key displays the particular key, or it will act like that. Coming to the defined part of keypad interfacing, the anatomy of a 4x4 keypad interfacing. So in 4x4 keypad contains 16 buttons arranged in a grid order, and that is 4 rows and 4 columns. In this 8 microcontroller pins required, and the matrix reduces pin count. The common pin assignments are R1 to R4 and C1 to C4. The R1 to R4 is the rows 1 to 4 and C1 to C4 is the columns 1 to 4. So it efficiently uses only 8 microcontroller pins. The 4 pins are connected to rows and 4 connect to columns. And this matrix design minimizes in-pin usage effectively. The defining part of keypad interfacing is the row-column scanning principle. The row-column scanning identifies a key presses efficiently. The microcontroller sets one row pin at a time to high. If it then reads the column pins, if a column pin changes state from 0 to 1 or 1 to 0, a key in that row and column intersection is pressed. This cycle repeats rapidly. First we have to set a row at time high. Then read columns, check for changes. If any check or any key is pressed, the key deduction will be takeover. Then the intersection found in the key deduction, and repeat the scan cycle through a rows. The eliminating false positive with debouncing. When keypad interfacing, at a time a multiple key will be pressed. For avoiding this, the mechanical buttons bounce when pressed, creating multiple rapid signals. Debouncing ensures only one key press is registered. So software debouncing adds a brief delay after deduction. Hardware debouncing uses filters to smooth the signal. The first is initial press. When the signal is detected means the software delay will wait for 20 to 50 milliseconds. After that only it confirms the presses of the keyboard. At the time it registers a single input. Ideate. Protecting keypad locks from brute force. Prevent brute force attacks by implementing a lockout timer. After a few incorrect attempts, disable input temporarily, so it will increase the lockout duration with successive failures. Always store the correct pin securely, not directly in code. Logging failed attempts set security analysis. The first one is the lockout timer. So if we wrongly pressed any key means after n incorrect attempts, so it will increase the delay. That means longer for more failures. And then secure pin storage. So it will avoid hard coding. The last one is the login attempts. For security analysis, these attempts will be used. Next one is the prototype connecting keypad to microcontroller. So our aim is we have to interface the keyboard and the microcontroller. So connect keypad rows to microcontroller, digital output pins. The root columns to digital input pins. Always use internal or external pull-up register to column pins. For example, Arduino pins D to D5 for rows and D6 to D9 for columns. The three logics are keypad rows and keypad columns and pull-up registers. So it will give a digital output and digital input and columns. The drive signal keypad rows and read key pressed and default high state. The last one is the prototype for code logic for key press deduction. The core decode defines the keypad out as a character array. It loops through rows, setting one active at a time. It then reads column pins to detect the active state. The intersection identifies the pressed key, which is stored in buffer. The first one is a define layout. So in this, we have to identify the key to character map. The second one is a scan rows. It is activate one by one. Third one is the read columns. So check for press. If I want to press some other button, means we have the interaction of rows and columns will be varied. The last one is identify key. So whether the key is pressed in particular row or column match. Displaying output on LCD or serial monitor. Once a key is identified, send it to your chosen display interface. Use CD print for LCD showing key 5. For serial monitors, use serial.print open brace close brace to display pressed X. Clear the display or buffer after processing the key. So LCD display directly display the character output. Serial monitor debugging and logging will be happened. Clear display after processing only the output will be showed in the clear display. Test and conclusion. Keypad mastery. Which pins are typically used for keypad rows? It is the RB03, RB7, RB47. That is the RB03 because it is a 4x4 keypad using. So RB02 R3 is used. And mastering keypad interfacing involves hardware setup, scanning, debouncing and display. This is a vital skill for various interactive embedded systems. The required pin is 8. Key supported is 4x4, so it is 16. The debounce delay is 20 to 50 millisecond. The maximum is 50 millisecond. Thank you.